I'll go ahead and. All right, so all the problems here are induction motor related. There is another problem on DC motors that you've got on the homework, but I think we've gone over enough of that. So, all right, so the induction motor stuff. So again, things that we're going to need here, basically. All right, so there's all these different frequencies that we talk about. So there's the mechanical frequency, which I usually put with an M, right? The stator electrical frequency, that's almost always going to be what? The stator, 2 pi 60. Okay. And then what I talk about is the frequency of the currents in the rotor, right? And that's related to basically the difference between the two moving fields. All right. And then the thing that's really important for us usually is this thing slip, which is really a percent difference between the speed the machine's running at and the synchronous speed, which is the fastest speed it'll do. All right. So the synchronous speed is the fastest speed the machine will move at. So what I wrote here, I said omega s is omega divided by p over 2. So usually the way we talk about it is in terms of speed in RPM. So the synchronous speed in RPM, if I had a two-pole machine, we'd be talking about, so it says omega s is omega divided by p over 2. So if I said a two-pole machine, what would be my synchronous speed in hertz? All right, this is omega, the radians per second, and we never really use radians per second. What would be the synchronous speed for a two-pole machine on a 60 hertz system? Yeah. So it's 60 hertz, right? So it says here omega s is omega divided by p over 2. So I could say fs, if I wanted to, would be f divided by p over 2. Just take the 2 pi's out of it, right? So this would be 60, right? So the machine, the fastest it can move is 60 hertz. So it goes around 60 times per second. If there's 60 seconds in a minute, that would be 3,600 RPM, right? So in the homework, you got problems where I think you got an 8-pole and you got a 6-pole. If it's 8-pole or 6-pole, is it going to be faster or slower than this? Slower, all right? And you can figure out which ones. All right, so real quick, this is our basic circuit model, right? This is basically a single phase circuit, and this is line to neutral, okay? Normally, when you give ratings on the motor, you give your ratings in line to line. So I think pretty much all the voltages I give you guys will be line to line, okay? And I usually make that clear, but typically you always see them being line to line. All right, so there's two things that are going on here. What I said is there's the power across the air gap. That's basically, we said this thing's like a transformer, so there's the power that's transferred into that resistor. That's the power across the air gap. That's equal to the mechanical power plus whatever the rotor heating is. So the mechanical power means how much power is actually going to some mechanical work that's happening, all right? Now, the problem I give you in the homework, I think the first problem I give you there is I say, well, that mechanical power actually has two pieces to it as well, right? So the pieces to that would be some losses, all right? Plus whatever power is actually delivered to the shaft, the actual torque times speed that would be delivered to a pump or a fan or whatever's connected to it. All right, the way we're thinking about this thing is it's all about energy conversion. I'm taking electrical energy in, some of that electrical energy is lost as heat. All right, and some of that heat is in this resistor, and some of it's in this resistor, but some of it is also in heat mechanically, meaning friction, right? So there's friction in the bearings that hold up the rotor. There's friction as the rotor spins, right? So only some amount of the power is actually delivered to the shaft. So when I talk about efficiencies and things like that, I'm saying, well, how much power is going into these terminals versus how much actually goes into turning that shaft? In other words, how much becomes real mechanical work. All right. We relate all that to the torque. All right. So we have this torque relationship here. All right. I think it's really important to us in all of these. We looked at a synchronous machine, induction machine, DC machine. In all cases, our circuit model had some reflection of what was happening in the mechanical side. For the DC machine, synchronous machine, it was somehow a voltage source, right? We had a speed-dependent voltage source. Here, I have this speed-dependent resistance. All right, that's happening. The reason we have that is because we don't really have an energy source on the rotor in the induction machine. How did the current get into the rotor on the induction machine? It was induced, right? That's where the name came from, right? It makes it a really rugged machine because it doesn't have that electrical connection that you have in some of the other ones. Okay. Now, I'm going to look today. So a key thing about how we use these things is we look at how they operate. So we look at the operating point. So I'm going to look at a pump, and you've got basically 2 or 3 problems, I think, on the homework that actually look at a pump, right? And what I'm saying is, you know, for reasons that are a little bit outside of what we do, if I have a typical two types of devices that we deal with pretty commonly, like if you go out and you get a job, very often, if you're working in the MEP industry, right, the mechanical, electrical, plumbing world, right, basically what you're going to do is spec-in motors probably quite frequently. Very often, you're going to be driving things like compressors, or you're going to be driving things like pumps or fans, right? If I'm driving a fan or a pump, it's a centrifugal device. The torque is proportional usually to the square of the speed, okay? Again, that's the physics of how a centrifugal device works. If I have a compressor, it's usually a constant torque load. Where I operate is where the electrical torque, right? Wherever the electrical torque equals the mechanical torque. What's special at that point? That's my operating point. What I know is special is Newton's law tells me what? At that location where the torque electrical and torque mechanical equal to each other, what's true at that point about the net torque? 0. So that's where I'm going to get a steady operating speed. And if the load torque, if torque mechanical changes, torque electrical will adjust itself so that they become equal to each other. It'll happen at a new speed, right? But it's always going to happen. So in this case, my operating point would be right there, where this is the torque. This is torque electrical. This is torque mechanical. Where those two things equal to each other, that's where will be my operating point. So I'd look down here and I'd find the speed at which that intersection occurs. Okay, so we're going to look at some examples, right? Important thing is for any of these problems, I got to determine an operating point based on the mechanical side of the system. Once I know that operating point, I move to the electrical side. I analyze the electrical circuit. For something like problem 1 on the homework, I told you what speed we were operating at. But in the other problem, I think in most problems, I told you what speed, right? I think in the last problem, I make you determine the speed where you're operating. Okay. Yes, so where I figure out what speed, and I can relate that speed to the slip. Right. So we'll do an example. So the machine, let's say I want to operate a machine here that, again, operating on a 60 hertz system. I guess I didn't write here the voltage. This is a 208 volt motor. All right, and that is line to line. We always give that stuff as line to line. 60 hertz, 10 horsepower. This would be pretty common for like a water pump in a building or something like that. So something that's circulating water around. And because it's operating a pump, the load torque is this beta omega squared. All right. And I don't think I wrote my beta down here, but I do have it. We'll go through it here. But basically, I gave you the parameters. I told you R1 and R2 are both 0.15. That's ohms. And then I gave X1, X2, and XM. All right, so X1, X2, and XM are the reactances, right, of the imaginary components. And because this is 60 hertz, everybody always gets confused about that. But if I talk X, if I've given you X, what have I given you? Omega L, right? And what was my omega probably? 2 pi 60. All right, 2 pi 60. So we'll need that later. All right, so let's look at the first case. I said in all of these problems, right? So back to this question. All these problems, I got to determine the operating point first based on the mechanical side of the system. So I'm going to start with this picture, all right? And I want to understand this picture for a second. So what I did here, this guy is my torque electrical. In other words, this guy is that 3 over, I never remember the equation, 3 over omega s, there we go. I2 squared times R2 over S. What I'm doing is I'm showing, so that's the torque electrical. This is the torque mechanical, the yellow. That's the load torque. So the torque mechanical is that beta omega squared, right? That. And what I'm showing down here is I'm showing omega M in RPM, revolutions per minute. So what's the synchronous speed in RPM for this machine? Looking at that picture, not telling you anything about how many poles or whatever it is. You should be able to look at that picture and know what it is. Well, you should be able to look at that picture and figure out what the synchronous speed is. 1800. Synchronous speed is always the fastest the machine can go, right? It's the fastest the machine can go, and how much torque do I provide at that point? 0, right? Because there's no currents being induced in the rotor. So basically this over here is my synchronous speed right there at that point. So how many poles is this guy? If his fastest speed is 1800 RPM, 4 pole, right? So this guy is P is equal to 4. All right. Common question that, you know, I've seen for like the FE exam is they'll say, I got a machine that's operating at 1747 RPM. Like this guy, just so we can see, I have highlighted the operating point. Okay. Common FE question would say, I got a machine that's operating at 1747 RPM. How many poles does it have? Before, because it's closest to that, right? It's always the actual operating speed is always really close to that. I could operate over here. However, doing that's really dumb. All right, the reason that's really dumb is the currents are going to be incredibly high over there. The current goes up and up and up as I go towards lower speeds. Okay. All right. So back to my operating point. This I'm saying is my operating point. Why is that my operating point? What's true at this point right here that I've highlighted? That's where torque electrical equals torque mechanical. All right. That's where torque electrical meets torque mechanical. So if you think about it, yeah. So what's true about steady state? It's a good question, right? So Newton's law always applies. Torque electrical minus torque mechanical. That steady state in general basically means where does everything become constant? So in other words, where does the speed become steady? So where the speed is constant, what's true about d omega by dt? It's equals 0. Torque electrical and torque mechanical are there. If I thought about this, so we're not going to do this, but if I basically at time t equal to 0, if everything was stationary, what I would see is at time t equal to 0, and this is a question I ask basically in problem 2. I talk about what's the condition to start this thing. What I see here is, for sake of argument, I didn't check this value, but let's say this is 70 Newton meters right here. All right, at that point, at a speed equal to 0, that's the maximum torque that machine's ever going to make when this thing is stationary at time t equal to 0. If I suddenly applied a set of voltages to this motor, right, the maximum torque this guy can make at 0 speed is about 70 Newton meters. Well, yeah, so let's say I had a load that basically was 80 Newton meters, right? Could I make it spin? Okay, so looking at this picture, if I want the machine to accelerate, what has to be true about torque electrical minus torque mechanical? If I want it to accelerate, what's accelerate mean? Speed up, right? So at time t equal to 0, if I'm stopped and I want to speed up and I want to start moving, what's got to be true about torque electrical and torque mechanical? Electrical has to be higher, right? This will work. Torque electrical 70 Newton meters, this guy's 0. What's going to happen is, if I were to do a simulation and look at this over time, what I would see is, over time, torque electrical and torque mechanical would basically go like this. And what I would actually see is if I look at the speed would basically be increasing, increasing, and then it would start to increase faster as torque electrical as torque mechanical got bigger. And then eventually it would reach a happy point over here where it would operate in steady state. Why does it increase like that? It's, if I look at it, it's basically in the circuit, it's the changeover as more current starts to go into, as current starts to split between the branches differently, is the reason for it. But yeah, but anyway, I mean, if you look at how it started, the important thing is if I had an 80 Newton meter load torque, mechanical torque, I would not be able to start it. It would be higher. It would be higher, right? So if torque mechanical is greater than torque electrical, it would basically just be stuck and it would stall. Right? The max amount of torque that you need for condition that mechanical is zero. Right, that's right. Yeah. So that would be my worst case scenario. And in reality, these things never totally look like this, where it's purely omega squared. Usually it's omega squared plus some constant or something. At low speeds, it doesn't totally go to zero. All right. Okay. And there's different ways that we design motors. If you really get into large motors, what you'll find is they have tricks to make this number get bigger. All right. And basically what they do is they do something special about the rotor. So there's different sets of rotor resistances. All right. But I don't want to get lost in that. What I see here is where this guy operates. What's it tell me? X is that, Y is that. So what does that tell me? X is that and Y is that. X is the RPM. So I'm operating at 1747.08 RPM. Torque is 40.7875 Newton meter. Okay. So my torque electrical and torque mechanical at my operating points apparently 40.7875 Newton meters. All right. And my speed is apparently 1747.08 RPM. So how would I figure out my slip? Slip is the percent difference from synchronous speed. You can go back to the equation, but basically if I told you what's the percent difference from synchronous speed. Yep. Yeah, 1800 minus 1747. You know, and I do it as in my equations as if it has to be done with radian per second frequency. It doesn't, right? If everything's in RPM or everything's in hertz or everything's in radians per second, it'll always work out. Yeah. If you only convert one of them, you have a problem. But if you convert them all to the same units, then you're good. Power and then speed, but it was in wouldn't that be in radians per second? It would, yeah. All right. All right. So when I do this, I get 0.0294, or what I would probably say is 2.94%. In other words, this guy is 2.94% lower than synchronous speed is where he's operating. And so what we see is, like I said, the range of acceptable torques is pretty tiny, right? Or the range of acceptable speeds is pretty tiny. This guy operates in that kind of a range. That's about it. So we often call this guy a fixed speed motor because he doesn't really change the speed much in going from no load. When I say no load, that's here. There's no torque being produced. Full load is there. This other curve I've shown here, this is actually the mechanical power. This is P mechanical. And I could look at that curve, or I could just do a quick calculation. What is the mechanical power? Based on what I have right here, I could easily calculate the mechanical power. I got everything I need. How could I do it? Torque mechanical times the speed. And I'd have to take that speed and convert it to radians per second to make that work. All right. If I did that, it works out to be, just to be clear, P mechanical, which would be the torque times the speed, works out to be, we almost always do the mechanical side in horsepower, works out to be 10 horsepower. All right. So what did I do to get that it was 10 horsepower? My answer would have been in watts, right? So if I did torque electrical time, so if I did that, whatever, 40.7875 times whatever the radian per second version of 1747 RPM is, I would have gotten a number that would have been like, what? If I got 10 horsepower, the number I actually would have gotten is 7,460 watts, something like that. All right, that's what I would have gotten. Okay. But again, mechanical side's always done in horsepower. All right, ask the mechanical engineers why they do it that way. Okay. All right. Case one. All right, let's say this guy is operating just like this. I want to figure out the slip, the torque, the current, the input power, the mechanical power, and I'm going to add one more thing, the efficiency. All right, and I got to be all fancy and go Greek on it, but it's the efficiency I'm asking. All right. All right, so we already calculated the slip. This was 0.0294. We already calculated the torque, which was 40.7875 Newton meters. So, and we figured out this was 10 horsepower. All right, help me out with the rest of this. How do I calculate the operating value for I1 and the input power PN? Where do I start?
Well, we didn't start where we have like R1, X1. Yeah,
Circuit.
you put the exponent R2 over S and series with each other, that would be
Yeah, basically what you guys, I do the circuit analysis now. Now that I know the slip, I do the circuit analysis, right? And I solve for the whatever current I'm looking for. All right. So let's what did I say? 0.0294. Some of my 9 didn't appear. All right. 0.0294. And I got to figure out, I got a voltage source connected to this thing. So what's the voltage source that I connect up to it? VAS. Yeah. So what were you about to say, John?
well, it's line to line.
Yes. So where did I, there you go. 208 volts. It was line to line. So VAS would be 208 divided by square root of 3. That, you know, I can get picky about the numbers, but it's basically 120. All right. That's a common voltage range, 120. And to be honest with you, usually a motor that's 208 can also be hooked up to be 480. Almost always they can be hooked up that way. All right. These are the parameters would be different. All right. But that's what I'm doing here. All right. So that means that I got a 120 volt source right here. The important thing is this is a single phase circuit model. There's 3 phases on this machine. Each phase is operating the same way. The only difference is there's, you know, basically a phase shift on all the voltage sources that are connected to it, right? All right, so I got this. If I want to figure out I1 is basically the current flowing in here. So let's call it I1 like that. Okay, so I think it's what Jackson you were trying to say. How would I figure out I1 now? Okay. Yeah, and let me call this R1 here. Yeah, so R1 plus JX1 in series with what? All right, J. Okay, somebody started their homework. There we go. Get that. And I got to plug in the value of S. And I did one thing wrong there. What did I do? That's not I. That's the impedance. Right. Yeah. All right. So if I wanted to find I1, I would say, okay, well, it's got to be whatever that 120 is. So my VAS divided by Z. Technically, Z is a phasor. And that would tell me it.
Does that necessarily matter?
Slip matters here. It's because basically what you're saying is the impedance is changing as a function of the slip. And it has to, right? Because basically what's happening is the machine is slowing down and there's a different frequency of the currents. This guy is basically reflecting how the mechanical operation of the machine is impacting the electrical operation of the machine. Okay. Now, in something like problem 2, I ask you, well, at starting, what's the torque, right? What's the current? At starting, what's the slip at starting? At starting, the slip is equal to 1 because I'm 100% off from my synchronous speed. And so this thing basically just becomes a circuit then, right? There's no over S in it, right? The idea is that I can go at starting. So in other words, at omega m equal to 0, S equals 1, and at synchronous speed, which is my full speed, omega m equals omega S, and my slip equals 0. At that point, when slip equals 0, how much current I2 is there? 0. Gets confusing because you look at it, you're like, well, R2 over S, that's infinite. Yeah, infinite means it's an open circuit, which means there's no current. Okay. All right, that's our approach. So the question I anticipate once you guys actually get to the last problem on the homework, all right, is you're gonna look at this thing and be like, what did he do? Right? So what did I do? What the heck is this thing? Well, what I ask you to do is I ask you to generate the curve that I showed right here, right? Like the torque electrical, the torque mechanical. I want to see that. I'm basically asking you to generate those curves. So what I did was, you guys tell me, what does this code do? Part I'm asking you guys to do is I'm basically asking you to go through and figure out I1, I2, RPM, tau electrical, tau mechanical. I'm asking you to figure those out. So what am I doing up here? You know enough MATLAB to know this.
Variables with values while also making it like it will have a number that will go into.
Making arrays of zeros. Yeah, that was, yeah, I like that. I'm initializing the variables to zeros, right? I'm creating an S vector, that's slip. An I1 vector, that's I1. I2 vector, tau electrical, RPM, tau M. I have a value of beta, right? This is the value of beta. This is the one, this is not for this problem, all right? The one that I'm doing here. This is actually from the homework. I copied this out of the problem 5 in the homework, okay? Basically, these are a vector of zeros, and there's 10,000 entries, all right? And what I'm doing is I'm looping through 10,000 times with the for loop, okay? So what we just said is that I1 equals, on the previous slide, we said I1 was VAS divided by Z, and Z was equal to, for that circuit, JX1 plus R1 plus JXM in parallel with JX2 plus R2 over S. All right, that was what we derived on the previous slide, just from circuit analysis. So how do I use that here? What's that? Yeah, right. I'll tell you what I do exactly is I figure out. So tell me what this for loop is doing. For k equal 1 to 1 to length of S, what's happening here, S of k? Yeah, so every time I go through this loop, what's going to happen to the value of S? It's going to change. What's it going to be the first time I come through? Really close to 0. It's going to be 1 over 10,000. Why don't I have it become 0, do you think? MATLAB would not be happy. Because I'd have R2, it's at some point when I run the calculation to get this, I'm going to have R2 over 0. And MATLAB's going to say not a number. And so the current, I don't know exactly what's going to happen. But so I start with a number really close to 0. Okay. So, all right. So S, the first time I go through this, excuse me, thank you. First time I go through this, S is going to be equal to 1 over 10,000. Last time I go through it, it's going to be 10,000 over 10,000. So what's that going to be? 1. All right, so I'm basically looping from S equal to 0 to S equal to 1. Okay. So I'm looping over all my slips. Down here, when I calculate the RPM, what do you think I'm doing? For the given slip, I'm figuring out what's the RPM. So what would be the equation that I would need to calculate the RPM? It would be slip equals what? Omega M, yeah, omega S minus omega M minus omega S. So solve that out. Except I'm going to solve it with this, right? Knowing what that is. So when I do this, right, I would actually say, well, yeah, so it'd be S of K. Omega S is just a constant. Synchronous speed doesn't change. This would be omega M of K. Because I'd be talking about during the case run through this loop, right? S is going to be a fixed number. I want to use the S value that corresponds to run number K, all right, or iteration number K. So when I do this, I would do it that way. Yeah. It's a lot. Yeah, I want to make it small enough, the step size small enough that I can see this graph pretty prettily. Maybe 1,000 would have worked. Maybe 100. But at some point it would be too granular. So that's 10,000 should be more than enough, basically. All right. And so what I would do is to do I1, I probably wouldn't do it all in one step like this. If it was me, what I actually do, R2 over S here, what I end up doing is I end up calculating, like, I don't know, I'll say R equals R2 divided by S of K. And then I calculate usually this guy by himself. And then I add that to this. And then I calculate I. So in other words, I break it up into multiple, like I probably have 5 lines of code to calculate this rather than 1 line. Why do I do that? Because it's a lot easier to read. Yeah. All right. So it's not just like this pile of parentheses that kind of adds up on you, right? That would be my recommendation, is you try to do it similarly. Then for everything else, like how do I get I2? Use the current division, right? So if I know this current, I can do current division to figure out the current that is in this branch right here. Okay. And why do I need that? Why do I need I2? To find the torque. Yep. All right. So, all right. If I run through this calculation and I do my numbers, I end up with I1 equal to 22.918 amps with an angle of negative 16.3023 degrees. All right, so I asked for the power, all right, and I asked for the efficiency. All right, so how do I get the input power for this thing here? How would I get P in?
It would be 3 times the output value voltage that the current I1.
Yeah, 3 times the magnitude of VAS times the magnitude of I1.
Times the cosine of the difference between voltage for the current.
You got it. All right. So I go through and I do that calculation, and in this particular case, I ended up with 7,924.6 watts. Okay. Now, when I ask for the efficiency is what over what? Efficiency of anything is what over what? Yeah, it's always output over input. So I would put P mechanical. That's the actual power delivered divided by whatever Pn is. Now, I said my mechanical power is 10 horsepower, but I obviously got to get these in the same units. So I switch them over. When I do that, I get that the efficiency is about 94.17%. That's pretty typical for a lot of motors. It's somewhere 94, 95%. In other words, what I'm saying is about 6% of the input energy becomes heat. All right. If you go into a plant and you touch a motor, it will feel warm. All right. Because we're talking about, so I said 6% of 7.9 kilowatts. I don't know, what's 1% of 7.9? 1% of this would be what, 79 watts, right? So, am I doing that?
Well, this 1% is going to get 9.0.
Yeah, why am I not doing it? So I gotta divide, yeah, so it'd be what? 79. Yeah, 79. All right, 79 watts, right? So 79 watts, if you ever touched a 60-watt light bulb, they don't make them anymore. They're too bad for us, right? But if I touched a 60-watt, it's hot, right? So they're saying that there's a lot of heat inside that machine, right? And if you did a thermal scan on it, you'd see that it would be hot. Okay. All right. So that's the efficiency factor, right? There's some power going into this thing, which is basically being converted to heat rather than into, think about everything as energy conversion, right? There's that much power going in. Some of that power is becoming heat. Some of it's being converted to mechanical work. 94% of it is being converted to mechanical work. That's what I'm saying here. All right. Okay. So now problem 3 on the homework, I basically say, well, let's hook it up to a variable frequency drive, which is what I talked about the other day. But the variable frequency drive, that allows me to spin it slower. All right. So I'm running it here at half speed. Okay. So how can I tell it's half speed? Synchronous speed's gone down to 900 RPM. Now, what sets the synchronous speed? Well, it's how fast the field from the stator goes around. So what did I change? To make this happen, I changed the frequency of the electrical side, 30 hertz. So I'm no longer applying a 60 hertz current to this thing. I'm applying a 30 hertz current to it. All right. What I'm doing is I've taken the frequency down to 30 hertz and I've made the voltage 1/2 of whatever it was. All right. So the voltage became line to line. It became 1/2 of 208. All right. I'm applying less voltage, less frequency. Okay. And what am I showing here? This is the torque electrical now. And this is the same torque mechanical. I didn't change anything about the mechanical torque, the same pump, right? But they're intersecting at a much lower point on the curve because effectively what, just to wrap our head around this, this was the curve that I had down here previously at a 60 hertz operation. I basically now have a curve that would be inside this, right? One interesting thing is if we look at this carefully, it ends up kind of intersecting over here. It ends up being just about as big, all right? You can see that actually has more or less the same torque down there. All right, it's pretty close, right? From reducing the voltage down and everything, that it has more or less the same starting torque. So what now? It's a little higher, right? And to be honest with you, those numbers are not like, you guys tend to look at numbers as if they were given to you by God, right? And they're truthful all the time, right? That's not ever true, right? If I took this motor and I ran it, we're talking about the resistances in that circuit are numbers like 0.15, right? You start running some current through 0.15 ohms, it pretty quickly becomes 0.3 ohms, right? And so those numbers would fluctuate a lot, right? So we tend to look at them as, well, they're around there, right? You would actually see them kind of moving around quite a bit. All right, so my operating point would be here again. Now, how do I find it? Well, the way I found it before was I basically took the data tip on and I looked for where they intersected each other. The other way to do it would be, so I'm going to basically do the same problem. All right, I'm going to solve for the same stuff in this condition, but I want to skip ahead because one thing I do in the code, I have it commented out, and this is the last problem. You don't have to do it for problem 2 or 1 or 3, but in the last problem, I have you figure out the operating point. So in other words, I'm trying to find this point right here. So how's that code working? What's this code doing? Well, let's go all the way inside here. So it's a while loop.
Both values.
Yeah. It's looping through the tau m vector and the tau e vector to find where they equal each other. It's starting at the end of the tau m and tau e vector. So it's starting here and here. And it's looking to find where does tau m become greater than tau e. So it's basically working through and it finds the point where they intersect. And so what's it going to tell me at the end? It's going to tell me the index where that occurs. So it's going to tell me a k value. In this case, I think it told me like k was equal to 145. So if I've got a vector, so when you solve this problem, what you're going to have is you're going to have a vector for your I1 and your I2 and your RPM and for your torques and everything like that. It's going to tell you the index of the vector where the intersection occurs. All right. So it's going to tell me where does that happen. So if I have an S vector, when this loop is done, if I did S of k, that's equal to where that's my operating point of slip. All right, that's the point where that crossover happened. It's telling me the index where that crossover occurred. When I did that here, what I found out was that my operating slip was 1.45%. All right, how would I figure out the speed then? How would I convert that to a speed? Yep. So I'd say my synchronous speed minus my mechanical speed that I'm actually operating at, divided by my synchronous speed. What's my synchronous speed now?
1.45% or
Well, all right, my slip is 1.45%. What's my synchronous speed? 900 RPM, right? 900 RPM. So when I do this and I calculate my actual operating speed, I came up with, in this case, 886.95 RPM. Okay. All right. So how would I figure out in this case? I want to figure out one thing that's important in this problem. Right, I've said this, the frequency to operate this guy, he's operating on a variable frequency drive. The frequency has been reduced to 30 hertz. And the line-to-line voltage has been reduced by half. Okay. If I had made the frequency 75% of what it was, then the voltage would have been 75% of what it was. They go together linearly. So that means effectively I've hooked this guy up now to a new voltage source. Really what it is, I've got a power electronic box where I can adjust the frequency that I create. But what's true about this now? I'm going to do phasor analysis. So let's call this I1. Let's call this R1. I'm going to do phasor analysis here. What's true about phasor analysis? What's required for phasor analysis to work? There's an underlying assumption we make anytime we use phasor analysis. Anytime you use impedance. What's the underlying assumption anytime you use impedance? Everything's the same frequency. Everything's in steady state at a constant frequency. And what's the frequency in this case? 30 hertz. Now the problem is I gave you X1, XM, and X2, right? So what do I got to do with X1 and X2 and XM? So I gave you those values assuming it was 60 hertz, right? So I got to basically say that it's whatever I had before times, 30 over 60 or something. So basically divided by 2, right? So I'm going to have to do that for all of them. Yep, right. Because basically everything's going to change. The inductance stays the same, but the X values are different. And again, in any of these power problems, we never talk about the L's. Typically, we talk about the X's. All right.
Normally X is the frequency.
Yeah. Yeah. But I'm on a VFD. I'm inherently changing stuff. Okay. So, all right. So if basically I would go through do the same approach as before. Let's say I want to figure out the torque and the power and everything like that. So I2, how would I figure out I2 if I knew I1? Let's just do the math. I1 and I got a current divider. So what's that current divider relationship going to be here? Yep. Yeah, remember to include the J's. Right, because the impedance includes the J's. And you would put in the value of S that we got previously, that whatever it was, what was it? 1.45%. Okay. So I run that number. I use that to get the torque. The torque electrical would be what? It'd be 3 over my synchronous speed, which is different now, right? Yeah. Yeah. And then the magnitude of I2 squared times R2 over S. All right. Now, if I run this and I figure out the input power, it's the same equations. I'm not going to write them out, but if I get the power input in this case, the power input works out to be 1.0104 kW. All right, 1.104 kW. Now, I can figure out the efficiencies and everything like that if I wanted to, but I want to stop for a second and say the efficiency of the power here is 1.01 kilowatts. In the previous problem, same motor operating at full speed, it was, what did we calculate? Yeah, so 7.924 kW. So the interesting thing to me is if I compare those numbers, so case one, I had 7.9, let's call it 7.9 kW. I don't want to flip back and forth. Let's call this guy 1 kW. So this is at half speed. What I see is that at half speed, I get 1/8 of the power. Why does that make sense? Nothing to do with the number of poles. The same number of poles in the machine. What was true about the torque of the pump? It was some constant times omega squared, right? So what would be true about the mechanical power delivered? Yep. Something to do, right? So how do I get from torque to power? How do I always go from torque to power? Torque times speed, right? So not only something to do, just a direct multiplication, right? So why does going half the speed make sense that it's 1/8 of the power? Yeah, because if I put in, but if I said the speed was 1/2 of what it was, it'd be 1/2 times 1/2 times 1/2, which would be 1/8. All right, so that's pretty significant saving. So one of the things I ask in the homework is, if let's say I had this pump operating 24/7, all right? So I had this pump operating 24/7. In case number one, how do I figure out the energy if it ran 24/7? It's a good question. How do I figure out the energy? Usually we calculate the energy in kilowatt hours because energy is the integral of the power, right? So what would it be? How would I figure out the energy? So yeah, so 7.9 kW times however many hours. So like in the homework there, I basically say it's operating 24/7. So I basically say 365 times 24, not 7. Like that. That would give me the energy, and then I calculate the cost. The important thing is, so I used a number that's a little, actually somewhat higher than what you'd see in North Carolina, but I did it in the homework. I do it for 10 cents a kilowatt hour, okay, which for somebody, I mean, at home, you're probably paying 10 cents a kilowatt hour. An industrial customer with a 10 horsepower motor is not paying that. They're probably paying more like 6 cents or 7 cents. But at 10 cents, it works out in case one. This guy works out to be about $6,914 or $941. In this case, if I can run it at 50% speed, it's about $885, right? So it's a decent savings. Now, why you would do that, basically you find out if it needs half the flow, I can run it at half the speed to make that work, right? And I get 1/8 of the power. So it's, variable frequency drive is a good way of getting energy savings oftentimes. That's why if you need control, you need it, but it's often a good way to get energy savings. All right, so I will stop there.